Okay guys, please turn to page 442, exercise 9.4. And now we are given an E field that propagating in free space, and then you are required to find the displacement current density, the JD, and also for the magnetic field, the H, and lastly to find the angular frequency, the omega. Okay, so as we discussed last time, we can simply find the displacement current density, the JD, by differentiating the D field, right, the dd over dt, and now we have epsilon dE dt. So since we are dealing with a free space medium, right, environment, so just put here epsilon naught. Okay, so now let's differentiate the E over T. Now you're going to have a negative 20 epsilon naught omega sinus omega t minus 50x, again in y directions or component, so it has unit of ampere per meter squared. Okay guys, so that's our displacement current density, and now we are going to find the H field. So as we discussed during last lecture, we have new ACL, which is our third Maxwell equation, which applicable to the time varying condition as here. So the curl of H is equal to the J plus dd over dt. Okay guys, this is our conduction current density, and then this is our displacement current density, our JD, right? Okay, that's our JD that we have obtained earlier. Okay, since we are dealing with a free space medium, right? So but there should not be any conduction process appear or exist within the environment of free space. That's why we're gonna have the sigma value will be equal to 0, which will have this term become 0. Okay, so the expressions of curl of H here is totally equal to the JD that we just obtained earlier. Okay, so now let's look at to the page 84, right, on your study book, page 84, under curl topic, and then let's focusing on the equations 3.43 for the case of Cartesian. So that table shows us how we can perform the curl of any vector in Cartesian coordinate systems. So from that table you can simply have this one, curl of H equal to, let's say, for the x component, y component, z component. So the first one is d over dx, d over dy, d over dz, and let's say H here we're not sure, right, the H will be in which component, so we just, let's say, we put all the components here. So we have the Hs as well, the Hy, and also the Hz. Okay, that's our first assumptions, right? We don't know yet which component the H has, right? Okay, so now we have just equal them to the JD that we have obtained above here. So now I'm gonna have negative y, right, negative and y there. So 20 epsilon naught omega sinus omega t minus 50x. All right guys, so if you can see from this equations, we know that, guys, this output of curl of H must be equal to this JD, whereby the JD now only exists in y component. So but we just focus on y component from these operations of curl. So just focus on the y component. whereby you can have here negative y, right? You just close this in the middle, then you're going to have a d hz over dx minus d hx over dz. Okay guys, and now it's equal to the negative y as shown above, 20 epsilon naught omega sine omega t minus 50x. Okay, so now we can simply derive this negative and negative, the y there and a y there. Now my question is, how do we determine which component that the h exists? Is it in z, is it in x, or maybe in y as well? So that question we must solve first, and which component the h that will exist. So we can simply find the component of the h or the e by applying this simple analysis, whereby we have a unit vector of axis of propagations is equal to unit vector of e cross unit vector of h. Okay guys, so that's a simple way, the simplest way we can use. So now we know that the e propagate and has a value in y component, so here we just put in y. Okay, and now we are going to find the directions of, the component that for the h that we don't know yet. So now we are, and how do I get the axis unit vector of axis of propagations? So guys, this one we can simply look at to the E equations or H equations. So now we have E already here. So from here we can simply know that the field of E actually propagating in the axis of X by looking at this. So that shows our axis of propagations, right? And then which one is it, in positive or X? Is it in positive or negative X they are propagating? So we can simply also know that from this sign, right? If shows a negative, it means that the wave propagate in positive X directions. Okay, positive X directions. If they say shows as a positive, it means that the field propagate in negative X directions. Okay, that's how we determine the axis of propagation for this particular field. So now we know already that the unit vector of axis of propagation will be in X, right? So using your knowledge before, so we can simply know that the unit vector of H field must be in Z. Okay, because the Y cross Z will have X, right? So we can simply ignore this term totally, because the H now only exists in Z component. So that's our main our term of interest. Okay, so now if I want to find the H, simple, just integrate for both sides. Okay, you can bring the S over there, so just integrate. Then you're gonna have to you're gonna have a DHZ, right? So now if you integrate at this right hand side, you're going to have again a negative 20 epsilon naught omega cos omega t minus 50x. Now we are integrating over dx, so I'm gonna have down here negative 50. Okay guys, so finally, if in terms of vector, you can simply have here, so we're gonna have 0.4 epsilon naught omega cos omega t minus 50x in Z component, and it has unit of ampere per meter. Okay guys, so that's our H field that we have just obtained by applying the third Maxwell equation. Curl of H is equal to the G J, right? The JD. Lastly, now we are going to find the omega, the angular frequency. So again, we can simply have the relationship between the omega with certain parameter that exists within these equations. So if you can see again, this equation not only give us the information about the existence of operations, but also it gives us the information about the beta value. Okay guys, the 50 here guys, the 50 that shows here, right, is actually our phase constant and we label it as beta. Is our phase constant, right? And it has unit of radian per meter. Okay guys, so the phase constant can be related to the omega as well by using these equations. The beta is equal to the omega mu epsilon. We are going to learn this one guys in detail in next chapter under wave propagation topic. So now since we are dealing with free space medium, so we just simply have here mu naught and epsilon naught. So now we can simply have your omega, just put here the beta become 50, and then down here mu naught, epsilon naught. Okay, then you're gonna have the omega is equal to 1.5 times 10 power of 10 radian per second. Okay guys, so I hope you can follow me, and all the best for your study. Thank you.